Good afternoon, everybody. We're going to start podcast number 2 on this section 14.2. It might be a little bit longer than the rest. There's a lot here in this section. So the first thing is we're going to talk about acid strength, and keep in mind that our shortcut formula for writing acids, let me grab a pen here, is the concentration of HA will have weak conjugate bases. So we have the cation with the anion, and acids are going to donate that cation. So what we have left for a conjugate is the anion. And then weak acids will have strong conjugate bases. So we're going to talk a lot about the percent of ionization of those acid molecules. All right, go ahead and turn over your page there. So our acids can be dilute or they can be very concentrated. And we have a high dissociation constant, which this means is that we have very weak bonds. So I'll develop that in a second. And if I have weak bonds, then I have a strong acid. So what this means is that I have a large Ka, and a large Ka means that it's going to dissociate and it's going to shift its equilibrium to the right. And then obviously the conversely is going to be true for something that's concentrated on the other end that has low dissociation is going to have a small Ka, so that means its equilibrium is going to shift to the left, and it's going to have really strong bonds. So if I have something that has high dissociation, it means that I can take my HA, I have a strong acid, it's going to dissociate into hydrogen ion plus the conjugate base. And here we need to remember that if I have a really strong acid, it's going to dissociate 100%. And so 100% means that if I have a concentration of 1.0 for this strong acid, the concentration of the hydrogen ion is also 1.0, and its conjugate is also 1.0 in terms of molarity. Now, this is not going to be true for something that has low percent dissociation. So again, if I have this, I do not know how much it is actually dissociating. So for here, we need to use our ICE tables that we learned in the last chapter. And that's what we'll develop here. Okay, so most acids are oxyacids. So I hope that you're focusing on that word oxy there. That means that there is oxygen attached. You can see monoprotic, diprotic, and triprotic. It just means the number of hydrogen that are there, 1, 2, and 3. We are going to focus on monoprotic acids. That's where the main emphasis is. The only thing that you need to understand with the diprotic and triprotic is that you will have a Ka1, meaning you have the first dissociation constant, which is what all monoprotic acids have. But then if it continues to dissociate, that's going to be stronger or higher than the Ka2, which is greater than the Ka3. So you just need to understand that if you have something that has more hydrogens, one hydrogen is going to come off at a time. It's not going to dissociate 2 or 3. Okay, oxyacids. So how do we determine the strength of an oxyacid? We can recognize it's an oxyacid because it starts with H. We have an oxygen there connected to something else. So if we have a large number of oxygens, we'll have a greater shift from the electron density towards the oxygen and away from the hydrogen, results in a stronger acid. We got to remember that when we say stronger acid, it means it's going to dissociate easier. It's going to break apart. So if I could give you the example of perchloric acid, which is HClO4, it's one of the strong acids, as you're going to see below. And if I just keep removing the oxygen here, I go all the way down to a hypochlorous. This is a very, very strong acid here, goes all the way down to a weak acid. Well, how does that work? So if I take a look at perchloric, I would have my chlorine in the middle, and I would have 4 oxygen around the outside. And then there isn't any more room on the chlorine to add that hydrogen. So what actually happens is the hydrogen attaches to one of the oxygen. I hope that makes sense to you by looking at this diagram, that these oxygens are going to be tightly held by the chlorine. That electron shift is going to go that way. And so then this hydrogen is going to be easily ionized, easily dissociated, easily broken off, which is going to make this a very strong acid. If I go to the other end where I had the hypochlorous, I have this, and both are strongly held in by this chlorine, both hydrogen and the oxygen. So this has a stronger bond. And because it can't dissociate, that means it's going to be a weak acid. So all of us have vinegar probably at home. This is an example of vinegar. We can smell it. It doesn't dissociate very much. It's a weak acid. So it holds in that hydrogen. Okay, you need to star this. I guess I don't know how to count yet, but you need to star the strong acids. You are going to need to memorize them. It's just assume that you know what the examples are for the strong acids. Hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, and sulfuric acid. So you need to know the names and the symbols both ways. So hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. Okay, water can act as an acid or a base. I think we mentioned this in the last podcast, and that means that it's amphoteric, materials that can behave as an acid or a base, and it's going to depend upon the situation if to become a proton donor or a proton acceptor. So if we take a look at water, and this is autoionization, that it is going to shift back and forth. In one case, it's going to become the proton acceptor of the hydronium ion, and in another case, it's going to donate it and have the hydroxide ion. So I can see that it can act in either direction, and this is going to be really important when we take a look at our pH. So we have another constant, you guys. We had Ka, we had Kb for acid and base. Now we have Kw for the dissociation constant for water. And our pH scale is all centered around this. So we know that Kw is a constant, 1 times 10 to the negative 14th at 25 degrees Celsius, which is room temperature. And the pH scale is the negative log, so we'll talk about that in the next section, and we're going to be able to figure out how the strength of the acid. Now, I want you guys to take a look at this equilibrium expression for water. Is still going to hold true that it's the hydrogen ion times the hydroxide ion, and we are still not going to put that over the reactants, okay? Because we do not include water in any of our equilibrium expressions. So we still have our products. And again, remember that I can write the hydronium ion, or I can use the shortcut and write the hydrogen ion. Either way, they mean the same thing. So I have my products over my reactants. My reactants are water. I omit them. So this is what my equilibrium expression is for water. And we know the Kw of that is 10 to the negative 14. Okay. So one last thing that I want to show you here on the next page, hang with me. It says for any weak acid, conjugate base. So a weak acid, should have maybe a comma there, for any weak acid and its conjugate base, or a weak base and its conjugate acid, we can say that the Kw is equal to its Ka constant times the Kb constant. That's something we need to remember. I think it is on our AP sheet, so that if we're given one or the other, we can find our Ka or our Kb. So here's our example. We want to calculate the hydrogen ion concentration. Remember, that's how we read that, hydrogen ion concentration, hydroxide ion concentration at 25 degrees Celsius. So then that means that I can use my Kw constant, and they gave us the concentration of my hydroxide ion. So remember that our Kw is equal to 1.0 times 10 to the negative 14th. Check this out on your AP sheet. That is also there, but it doesn't say what it all is, so you know have to know when to use it. Well, I can simply substitute that in. So I have 1.0 times 10 to the negative 14th. I want to know what my hydrogen ion concentration is. I'm given my hydroxide, so I can go ahead and do my algebra, and I can calculate that my hydrogen ion concentration at 25 degrees Celsius with this given hydroxide is 1.0 times 10 to the negative 9th. Should have been able to do that in my head. And then one last thing that you should take a look at is, here's my hydroxide ion concentration, and here is my acid. So comparing those two concentrations, I can see that my hydroxide ion concentration is greater than my hydrogen ion concentration. So that tells me that I have a basic solution. You could also find the pH of that, which we're going to do next, but you don't need to do that if you know and use your KW constant. All right, that's it for today. Have a wonderful day.